Okay, so this is the last talk here, and it's about if we can actually predict the structure of matter. And actually, I need my pointer now. Oh, did I? And I'm working here at the chemistry department, but I already tell you that this is a very interdisciplinary field. Usually you find especially this theoretical part happening both in physics and chemistry and material science as well. And I'll stand over here. The reason for that is that the question we are worried about is how can we go from a collection of atoms, as I show here, for example, carbon, nitrogen, and hydrogen, which are color-coded in different colors, to actual materials. For example, how do these atoms, under certain pressure and temperature conditions and subject to certain reactions, they form a solid, as you see here, or if you put some oxygen atoms, it can form, for example, a biomolecule, as you see here, or if you take, you know, as it's very famous, oxygen and hydrogen atoms, under certain pressure and temperature conditions, they form a liquid, which is in fact water. And understanding this is all about understanding chemical bonding, I mean, and this we understand nowadays through quantum mechanics. So I'll tell you a little bit about that. So in quantum mechanics, atoms are actually kind of fuzzy entities, like you see here. They are described by something that we call a wave function that I here call psi. And in 1926, Schrödinger, he proposed this equation, which is the Schrödinger equation in its time-independent form. And this equation simply says that there is this H here that I say it's a kinetic and it's a Hamiltonian operator. It has kinetic and potential energy operators, and it acts on this wave function, and it's equal to something that is the energy times the wave function again. And this looks like a simple equation. It's actually not. But in fact, all interactions between all atoms is given by this equation, or its version including relativity, which is the Dirac equation. It's so much so that already in 1929, Dirac had this famous quote, which I read here. So he says, "The fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known," by this equation here. But there is a catch. In fact, the difficulty lies only in the fact that the application of these laws leads to equations that are too complex to be solved. And they are really too complex, and this is due to the dimensionality curse that we say they are really too high dimensional. Nowadays, it has been a long time now, since 1929, we can actually use computers and quite accurate approximations to these equations to make predictions coming really solely from, so to speak, the first principles of physics or quantum mechanics, and I show a bit how we do that. So we need to do some approximations, as I said, and the approximations that we do, one is a very famous one. It's called Born-Oppenheimer approximation from 1927. And there we say, well, let's decouple the nuclei of the atoms from the electronic cloud. So this fuzzy thing here around, I call the electronic clouds, and they're the nuclei. Let's decouple them and not let them talk to each other. And this is okay to do most of the times because the mass of the nuclei are kind of 10,000 times the mass of an electron, and they move in very different time scales. So it's okay to say, well, I move these guys, but these guys, they don't talk to each other. We do then a further approximation. We forget that the nuclei are actually fuzzy things as well. We make them like hard spheres. We say they're classical particles. They have nothing to do with quantum mechanics. And we let only the electrons be the quantum mechanical things. And that's also kind of okay to do most of the time because lighter particles are much more quantum than heavier particles. And this also comes from quantum mechanics. But still, we still have to solve this Schrödinger equation again for the electronic degrees of freedom, and it's still a very, very hard, if not impossible, problem to solve, because the problem that I mentioned here is that one electron moves in 3 degrees of freedom, 2 electrons in 6 degrees of freedom, and then 1 mole, 10 to 23 electrons move in many degrees of freedom. So we need to find approximations to solve that. We cannot solve that even in the computers we have nowadays. And there are many ways to solve this. Some of you might have heard the Hartree-Fock method, coupled cluster method, configuration interaction, and so on. But there is one method that is called density functional theory, which I tell a little bit more in the next slides, because this is the method I think that allows us today to treat the larger sizes of systems within this quantum mechanics theories. So in density functional theory, it was proposed in 64 and 65 by Hohenberg-Kohn and Kohn and Sham. And it's a nice thing because they show that it's possible to obtain any quantity, any property you like from your system from looking only at the electronic density and not this full wave function that I've shown in the slide before. And this is nice because this thing doesn't have all those dimensions that I was talking about. It has only 3. So it's great, but although this theory in principle is exact, in practice it needs a lot of approximations. And we then solve the resulting quite complex equations numerically with the aid of really big computers. So our work is usually like this. We sit in front of a computer, then we send calculations to these really big computers. This is the Archer supercomputing cluster here in the UK, and gather results back. So this is what we do the whole day, sitting in front of a computer. And what we can do there, I just show a simple example of what was my work some years ago. So if you take a simple peptide, a peptide is a small protein. And in this case, it's a simple one. A protein is built by amino acids. There are some molecules. This is built by 15 alanine amino acids. These are these ones here. And then in the end, it has another amino acid. It's called a lysine, and it goes here. And the big question is this molecule helical or not? Can we tell that? And experimentalists can actually look at this molecule. Not with microscopes, but they can measure the vibrations of these molecules by measuring their infrared spectrum. So this is what I show here. This is an experimental infrared spectrum of this molecule. This is the intensity, this is the wave number. This is the frequencies with which essentially this molecule vibrates. And they have these peaks and so on. And they want to know, well, what is the actual structure of this molecule then? And then we can aid them with simulations. We can see what quantum mechanics actually say. And you don't need to understand this formula, but by simulating this molecule with these methods that I have just shown and measuring the dipole of this molecule, this is the Fourier transform of the dipole-dipole autocorrelation, you can actually simulate exactly this infrared spectrum that the experimentalist can measure. And this molecule is not just stopped in space. You see it actually moves. And from this signal, we can reconstruct what you see here in red. And what is important here is not really the intensities or the heights of the peaks, but their positions. And you see that their positions that we simulate are very, very the same as the ones they see in the experimental spectrum. So we can say, well, yes, this molecule is actually helical. It adopts this structure, and we have this knowledge now. So that's very nice, but there's still a lot to improve. I mean, these are very costly calculations. We can only treat sizes of molecules that go up to hundreds of atoms. And the treatable timescales we can go, it's hundreds of picoseconds. 1 picosecond is a millionth of a second. So it's really, really short timescales that we can treat. And it does rely on approximations that do not always work. So we have to do a lot of work on better approximations and on improving algorithms and also improving computers, to treat larger sizes and larger timescales. There are times when this Born-Oppenheimer approximation breaks as well. And there is one interesting point, which is what I'm working with more now, is that, you remember you said we usually treat the nuclei as classical particles because they are just so much more massive than the electrons. But this is also not really a good approximation all the time. And I tell you one quite important time when it's not a good approximation. If you take here, this is the pH of water. So it's a measure of how acid the water we have is. And as many of you may know, the pH of water is usually 7. But you can actually calculate what would be the pH of water if all the nuclei in your water would be classical. And in this graph here, this is the number, so it would be around 8.5. So while you would be quite alive drinking this water, you would die immediately if you drank classical water, so to speak. So it is important to simulate these effects sometimes if you want to be more realistic. And the way you do it is actually through these path integrals here. It's a great method where that was proposed actually by Feynman where you see that there is a relationship between the properties of a quantum mechanical system that can be mapped on a system that is what we call a ring polymer. It's several repetitions of the original system connected by springs. And this is a much easier object to treat, and we can use this then to simulate also the quantum nature of this nuclei in your molecule. And as I said, this has important applications also in these when you want to get information about structure. So the same thing as I've shown you before, so this infrared spectra, which measures the vibrations of your molecules. If you take liquid water, for example, and you again do a simulation of the infrared spectrum without including the fact that your nuclei are also quantum mechanical objects, you have a signal that is this thing in red here, while if you do include all of this quantumness, this is shifted, and this is quite an important shift. I mean, experimentally it would make a big difference to tell you what is the structure of the material you're looking at, and so on. So this is the type of things we can do right now, also with the aid of computers. And just as a last slide, what is our quest for the Holy Grail in this field? So it is actually to achieve a more accurate description of materials and molecules, really all, if possible, based on the first principles of quantum mechanics, because we actually know these equations and we have to use them wisely, I think. And of course also enhance our understanding, because if we understand very well what is the physics behind all of these material science, if you like, we can really enhance our predictive power to design new materials, drugs, nanotechnological devices, and so on, all inside a computer, so in silico. So thank you very much.